Hello, everybody. So today we have with us Fernando Buitrago. I'm sure most of you already know him. So he had an international IEC fellowship to work in Nottingham. And his supervisor was Nacho Trujillo. Then he did a postdoc in Edinburgh, and now he's working at Lisboa, where he's also lecturer. Yes. And today he's going to talk to us about relic galaxies. So please, go ahead.
Thank you very much, Alicia. Thank you very much to all of you for coming over. Of course, for me it is a pleasure always to come to the ISC because here I feel at home. Before starting, I would like to say a couple of things. First of all, I would like to acknowledge several people for my time here. Jesus Falcon, who was the person who managed everything. Ali Reza, with whom I am learning these days what it is spatial modeling. And also, for this very talk, Benjamin Montesinos, because without him, I couldn't finish this work in time because several months ago we were managing together the SIA meeting. So thank you very much to the three of them. Also, I always seize the opportunity for introducing the audience what it is the Institute of Astrophysics and Space Sciences, because many people don't know about it. So now in Portugal we have fusion, what it was the Observatory of Lisbon and the Observatory of Porto into the same institution. Okay? So we are the largest astronomical institute in Portugal, or at least the largest one when it comes to observational astronomy. And finally, before starting, yesterday in Nacho's talk, I realized that all the questions were coming from senior people. I would like you to interrupt me as much as possible, and especially the students, please. So this work is going to be about relic galaxies. The main effort was done by me and Ignacio Ferreras, who, as you know, is also a staff nowadays in the IIC, and also his PhD student James Anzopo, which is in the IEC, located at the IEC at the present time, and also some other friends like Lee Kelvin and all the GAMA collaboration. So if you go to the Oxford English Dictionary and you look for the definition of relic, you can find just this: an object surviving from an earlier time. When it comes to galaxies, what we are referring is that if you try to look for an image of a high-redshift galaxy, you just have a bunch of pixels. And ideally, we would like to know in full detail how these objects are. For example, for this very galaxy image, I was looking about objects like this during my whole thesis. And I was always intrigued about, these are just how many? 100 pixels? How are these objects if you have the luck of looking at them live, looking at them very, very close? And I was always wondering about that. So if we happen to find these galaxy relics, we assure that we have windows to how things are in the high-redshift universe. I am not going to bore you today with many details because the ISC has been leading this role of understanding more about massive galaxies and about galaxy relics throughout the time. And here we have just a bunch of people from the many who have worked into this topic along the years. And I'm going to start this talk from the point that Nacho left yesterday. So the most massive galaxies of the universe, usually, as you can see, elliptical galaxies, living in the big megalopolis of the universe, which are the clusters and superclusters of galaxies. So, yeah, huge ellipticals and very rare. This is the vision all of us have, regardless we are extragalactic astronomers, solar astronomers, stellar astronomers, so forth. However, since I started my PhD a decade ago or so, we can tell nowadays that there are several things in which are well established from the knowledge of these objects at high redshift. And I would like to highlight the three. First of all, a concept which is called downsizing. These galaxies are already present at high cosmic distances, say 10, 12 gigayears ago. And this tells that these galaxies have undergone an accelerated evolution in comparison with low mass objects, right? So if you look at that at those times, they have already well set morphologies, their kinematics are also very well defined, and so forth. And as a matter of fact, some of them are already dead and dead at those cosmic distances. So for example, here you have the spectrum for this object, which is you can tell it's very massive galaxy, a redshift about 2, and it's from X-shooter. You can tell that almost no light in the blue part of the spectrum, a very well-defined 4,000 Armstrong break, and then you can tell without any problems the continuum of this galaxy. But what it is very fascinating for the community is that these galaxies are, first of all, extremely small, with effective radius smaller than 1-2 kiloparsecs, and they look like disks. You can tell that this is a perfect disk that fits into the slit, and here, well, as we are so high redshift, and we are also speaking about very small objects, it is hard to tell the morphologies, right? You can tell that they are disk-like, regardless whether they are using GTC or, for example, adapted optics observations. These combined factors being very small and most of the times being red objects had made that the community usually call them red nuggets. Beautiful name. The spectrum, I will say that this galaxy is not especially compact. I can't remember at the top of my head the size, but it must be something like 2 kiloparsecs. So it is not the... Exactly. And you know, it always depends on what you call compact. But one way or another, for this very object, if you go to redshift 0, the expected size is something like 5 kiloparsecs. So this must be an outlier, a factor of 2 outliers, but you can find even a factor of 5 outliers of that. And I do love this spectrum. You can tell absolutely everything about this object. It's X-shooter, if I remember correctly, 12 hours integration time. On the other hand, if we move to the local universe, for example, here I am showing the mass-size relation by Lee Kelvin up to redshift 0.6. So here you have in the y-axis number of galaxies, x-axis the mass of the galaxies. You can tell that the high mass n is dominated by this red line, which are the ellipticals. And at the top of that, we are speaking about the part of the galaxy mass function which is dominated by the exponential decay. So these galaxies are very scarce in the local universe. So that made people think, again, 10 years ago or so, for example, in this wonderful, wonderful, wonderful paper by Andrea Cimati, that superdense massive early type galaxies with very small radii are extremely red at Z0. However, it might be possible that they hide in the cores of present-day ellipticals. Well, people thought that the local universe was devoid of these objects. But Nacho said, no, I don't believe it. This is a lesson I learned at the beginning of my PhD, to always question what the people take for granted. Nacho saw the same paper as I read, and he said, no, I don't believe it. I am going to go to Sloan, and I'm going to test this idea. And here you have the size of the galaxy, here in the x-axis the mass of the galaxy, and there were several objects that were extremely compact in Sloan, the same as the high redshift galaxies. Forget about the stars, because the stars are AGN. We are speaking about these gray points over here. And if you look for the images of these galaxies, so they are kind of point-like, but a bit more extended. So they were really galaxies which were analogous to the ones, to the red nuggets at high redshift. The problem was that when Alex, for example, was trying to analyze the spectra of these galaxies, they realized that they were not the galaxies coming all the way from the high redshift galaxies because their stellar populations were very young. So here we were speaking about the last tail of galaxy formation, of massive galaxy formation at low redshift. But anyway, very interesting objects because they were similar to the ones that we find at high redshift. Then some papers highlighted that the reason why we haven't found these objects in the local universe was because we were not looking at the right places. These objects must be found in galaxy overdensities. But this looks like counterintuitive because, you know, galaxy clusters, for example, is where you have more galaxies. So many galaxies imply many mergers and therefore big sizes for these objects. Well, the thing is the very large internal velocity dispersion of clusters prevent these galaxies from merging. So it is a good idea to fall early on in a galaxy clusters because, believe you or not, at the end of the day, you are not going to merge with your neighbors and you are going to preserve your high redshift properties. And some theoretical work, for example, by Martin Stringer here in the IAC, and also Claudio, show that most of these objects in the simulation, 82% of them, were in clusters of galaxies. So, apparently, you need to look for something which is ultracompact and something that must be located in a galaxy cluster. There was a quest in order to find the first of these objects, and here you have the first image of how a red nugget looks like. This one, there was extensive work about that. I suppose that you have heard about this object many times here in the IEC, NGC 1277, located in the Perseus cluster, 73 megaparsecs away from us. And you can tell that it is kind of disky, but not very clearly. Actually, for me, it looks like an S0. You have the dust lane in the middle. And it is featureless. You can't really tell much more about it, except that it is a red object. The first time I looked at that, and it was not this paper, it was the very first one, I was on the verge of crying, to be honest with you, because my wish was fulfilled. You know, finally I could see one of my high redshift objects in reality how it looks like. And as we are making the comparison with Indiana Jones, I felt like laying at the end of the Riders of the Lost Ark. And in order to show you that it's really located in a galaxy over density, here you have the Perseus cluster, the big elliptical dominating the cluster, a satellite elliptical, which is also very massive, and here it is this object. So it's a satellite of a satellite. So something very odd. However, these relic galaxies have proved to be a real treasure trove for galaxy evolution studies because, first of all, they have very strange kinematics. So they rotate like a spiral galaxy, 200, 300 kilometers per second. And their velocity dispersion is also very high. You can tell that in the center is 400 kilometers per second for these objects. Then they host supermassive black holes, which are outliers in the mass of the black hole versus mass of the bulge relation, but by a lot, right? Here we are speaking about 3, 5 sigma outliers in this relation. So very large supermassive black hole for the stellar mass that these objects have. Also, that they seem to host a bottom-heavy IMF, meaning that they have a huge overdensity of very small stars at all radii. And also the latest paper by Mike was telling that the NGC 1277 was the first galaxy in which we saw a unimodal populations of globular clusters. So for example, the nearby elliptical that I will show you before, NGC 1278, is showing the typical bimodal distribution of globular clusters. Some of them some of them blue, some of them red. However, in NGC 1277, we just have one bump which corresponds to the red globular clusters. So this galaxy is indeed a relic coming from the high-redshift universe. And but just as a joke, people really like to think about supermassive black hole. I found this picture, Googling image information about NGC 1277. And as we are now featuring the Queen movie, why not to show a bit of Freddie Mercury? And coming again with Queen music, if we want to investigate the big endeavor, which is going to be the intermediate redshift for these galaxies, and I'm telling you that it is a big endeavor because you must think of that when you are looking at high redshift for this object, you have a very large volume to survey. And when you are very close in the local universe, it's easy to spot things because they are very close to us. The problem is, if we try to find more of these relic galaxies, it is a real quest because at intermediate redshift, our cone of light implies that there is little volume to survey, difficulting very much the identification of this galaxy, and we really need to go for very large areas of the sky in order to identify some of these objects. In my personal case, in our latest paper, we have investigated the whole GAMA survey, which is 108 square degrees. So if the size of the full moon is half a square degree, we are speaking about 360 times the size of the full moon. But we need a very deep imaging in order to tell whether these galaxies are really compact. You can tell that the Sloan images were kind of fuzzy. Here we made use of KITS and Viking surveys, which are 2 magnitudes deeper than the Sloan for the photometric. And also for analyzing the light of these galaxies, we don't only use normal stars as PSF for our observation, but we also made use of weak lensing ones, just as a proof of concept to see whether satellites that Euclid are going to be good in order to identify these objects at intermediate redshift. And the answer is yes. The PSF are small, but for these objects that are very compact, they are good enough in order to tell the galaxy sizes. And finally, we chose Sloan because of the spectroscopic completeness. In SDSS, there was another problem that these galaxies were systematically missed because it was very hard to put fibers, spectroscopic fibers, very close to each other. They were colliding problems. Here, we assure that by using gamma, we have a very high completeness, close to 100% for bright objects in our sample. So the questions we wanted to answer in our study was that, do these galaxies really reside in galaxy overdensities? What are exactly their number densities? Because with very few cases, it was not very well constrained. And finally, how many of these relic galaxies we have in comparison to something which are very compact? And I want you to reflect about this. So before, when I was speaking about this earlier paper by Nacho, we were speaking about just massive ultracompact galaxies in the nearby universe. So objects which are very massive and which are very small, but the stellar populations are young. So they are not the red cluster, the red nuggets that we are finding in the high redshift universe. They are objects that happen to be formed late, but they resemble the things that we are looking at high redshift. However, a real galaxy relic must be something which is very small, very massive, and very old. These are the objects which are really coming from the high redshift universe. Ali Reza, sit down wherever you want. We are among friends. So, we are trying to look for both objects in this study, something which is very massive, something which is very small. But if possible, it would be super nice to identify these very old objects because these are the guys with the most extreme conditions, as we were speaking about before. Yes, of course. Because Not really, because if it's not very small, the problem is that you mix the information from all the other galaxies that have merged with these objects. Yeah, but think of a big massive elliptical. Think, for example, of a big elliptical galaxy. At all cosmic distances, it's something which is very old. It's 12 gigayears. We know that by spectroscopy of local elliptical galaxies. However, you don't have the information of just the thing which has formal very high redshift. You have the information about this object and about all the other mergers. That's why by looking at these three conditions, you are sure that it's really coming unaltered, untouched from the high redshift universe. But please be critical, Mark. That's why we are here. So these are, by solving 180 square degrees, the 29 objects that we have found with this selection criteria. The sizes are smaller than 2 kiloparsecs in at least 2 photometric bands. The stellar masses are greater than 8 times 10 to 10 solar masses. And well, I included also these objects because these objects are the ones which could get into the sample because of our mass uncertainties. And you have always to think that these masses come from Chabrier IMF. If you think that in reality these galaxies have a bottom-heavy IMF, the masses are always higher, okay? Because for the same luminosity, you have even more stars. And also, I highlighted here with the red squares those objects which are relics, which are, we have information that these galaxies are old, but we don't know exactly how old they are. I will come to this point later. Well, here you have the sizes for all the different bands. Go to the paper if you want a little bit more information about all the details of this study. Let's start with the plots. First of all, the mass-size relation. Here you have the effective radius of the galaxy, so the radius which encompass half of the light coming from these objects versus their stellar mass. And you can tell that if we compare our data points with the local size-mass relations, they are 2-3 sigma outliers, as we were expecting. If you try to look for the morphologies of these objects, it is kind of hard, as you can tell here, right? Because how can you tell whether this object is a disk or an asteroid? We rely on Sersic function. So we fit Sersic function to these objects, and if you are greater than a certain value, you think that you are an asteroid. If you are smaller than a certain value, you think that you are a disk. But we confirm that most of these galaxies seems to be disk-like objects. I would like also to draw to your attention about a funny fact here. As you can tell, the majority of these objects have very close companions. Well, some of them, but just 2-3, are, let's say, isolated. But in other cases, you can find very massive companions, like NGC 1277. But in other cases, and this is something that we don't really understand, in projection, you have also very small objects very close to our target. And when most of your sample is displaying the same feature, it makes you doubt whether this is a coincidence or not. But again, this is a detail that we don't fully understand. If you try to investigate the mass profiles of these objects, the mass densities of these objects, both in 2 dimensions and in 3 dimensions, you realize that for the disk-like objects, which are these blue histograms, they always seem to be denser than the disk are always seem to be denser than the spheroids, which are the red histograms. So how come that also that the disky massive ultracompact galaxies are systematically denser than the spheroids? Okay, this is something that we will investigate in the future, but we have evidence about that in our paper. For example, with the spatial modeling I am learning with Alireza, I hope at some point to investigate the 3D spectroscopy of these objects and try to come with an answer for this conundrum. And if you want to have an idea about the stellar population of these objects, yep. Mm-hmm. Yep. However, I will say that they are indeed fast rotators. Many of them.
In the center.
Mm-hmm. Yeah, but I can't remember very well now the capillary. Yes. Well, this is your study, right? This is what you did with Anna.
That one, you see? So you can see that the rotation velocity is, for example,
200, 300,
which is
yeah.
typical of a disk.
Yep, indeed.
Okay? But if you look at the velocity dispersion, it's even higher than in an spheroid.
Yep.
Okay?
More or less.
So
But a slow rotator in a... Correct me, guys, if I am wrong. Jairo, for example, people that know about 3D spectroscopy more than me, but the slow rotators have a B over sigma of the order of 0, while for fast rotators you have things of 1, 2. So these objects will be catalogued as fast rotators. Oh, yes.
So
Yeah,
these
yeah,
are
yeah.
disks.
So they are not disk per se, but they are, we call them, by looking at the images, swollen disk, early disks. So they have a disk. This is what we can tell, or something exponential inside. Another line. If you join this information with the fact that they have also large rotational velocities, yes, you can say that they are disk-like, but they are not exactly disks as we understand it in the local universe, of course. Exactly. Swollen disk. This is my favorite expression for them. Here. So the thing is, in order to have an idea about the stellar populations, here you have a spectral feature plot, the 4,000 astron break versus two other features, and you can tell that things that are on the top of the plot, at the top of this pink division, you can tell that they are older than 2 gigayears from previous studies by Ignacio and by Alex. So we know that approximately 1/4 of our sample, as I told you, are galaxy relics. The other 3/4 of the sample are massive ultracompact galaxies, but we don't know yet exactly how old are the stellar populations. We need also better spectroscopy in order to tell us that. Because the funny thing is that by using gamma, we have a very good idea about the redshift of the galaxies, but the redshift are not good enough for telling us their stellar ages. We have just a single Sloan spectrum for them. But for the only Sloan spectrum that we have for a galaxy relic in the sample, the stellar population seems to be 12 gigayear old. So this is a crude division, but we believe that it is more or less true. And if you try to look at, yes, please, Jorge. No, this is 2 gigayears exactly. But my point is that this division is older than 2 gigayears, younger than 2 gigayears. Only 2. Yeah. But I'm telling you that for the only object in which we have IDSS spectrum, which is one of these blue points.
What is the typical redshift of these objects?
They are between 0.02 and 0.3. So most
very,
of these
very
objects are located between 0.2 and 0.3.
But this is not very old, really.
This is not very old, exactly. So we can assure 100% that they are relic galaxies. But while Yes, of course, of course, of course. So they are 2 gigayears older than 2 gigayears at redshift 0.2 at redshift 0.3. This is what is this what you are asking?
I mean, because every galaxy is a different redshift.
Yes, every galaxy
So
has a
you should
different redshift.
take into account this redshift correction in the age.
Yes, of course, of course,
Is it,
of course.
is it there? Shown
Yes,
there?
yes, it is there. It is there, the redshift correction, of course. So while we say that these galaxies at their redshift are older than 2 gigayears, younger than 2 gigayears. But for the only galaxy in which we are able to measure well the stellar ages, we can tell that it is very old galaxy indeed. Okay? But this is what we can do with the spectra we have at the moment for these galaxies. Say that again?
You have photometry.
We have photometry.
And
yes.
even from the photometry, I
But
guess
the
you can
photometry
say
is
something
not
about
that
the ages.
great, right? In kids we have 4 bands. In biking we have another 2, 3, and then you have sloan. This is what you have. So yes, you can run your favorite code over that, but it is not going to be super well constrained. What is? You will do better than 2 gigayears, but it's just to have a division telling you this is all, this is the young. At this stage, for us, let's say it is enough. Of course, we will try to do things properly at some point.
I think that I mean, the fact that it's above 2 or below 2 is very simple. If you have a very bad spectrum, this is the only thing you can say. As simple as that.
I don't want to speak badly about the spectra in our sample because thanks to
Yeah.
our spectra we have this study, but
Yeah.
there are some
Yeah.
little problems, let's
I
say.
mean, it's very difficult to distinguish the ages above 2 if the spectrum is not high enough.
Exactly. By the way, I was only interrupted by senior people again. I want the students. And when it comes to the environment, so to the places where this galaxy lives, the results are kind of no sense. By the way, I haven't told you about our data points. So blue means disk-like object, red means spheroid-like object. A small point means that they are not very massive. These objects between 6 and 8 times 10 to 10 solar masses. And big points means something which is very massive. Okay? So you can tell that by looking at the distance of these objects, the cluster-centric distance of these objects, so their distance from the center of the cluster, or you know how big the overdensity of galaxies is, there is no trend with the mass of the object or with the morphology of the object. These galaxies seems to reside at all cluster-centric distances. These galaxies seems to reside in all kinds of galaxy overdensities, for something which is more group-like to something which is more cluster-like. So this thing about these galaxies are living in galaxy overdensities is not true. You can find them in all kinds of environments, adopts with the theoretical predictions. But you must think, yes, please, Claudio. I like you. You are the typical student I was thinking of.
I think it's a problem of semantics.
Yep.
Everyone will tell you that everything that is above 10 to the 13 is in a large overdensity in the universe. It's where you put the cut.
I think that the local group is more or less.
I mean, if
in
you
this
talk
region.
to any cosmologist, that is a large overdensity in the universe.
Mm-hmm.
Overdensity in total mass distribution. So I think it's question of semantics.
All right, but one would.
Everyone define things as they like, but
If you remember the beginning of my presentation, I was telling you these galaxies, in order not to merge with the rest of objects, should fall very early on in overdensities, and overdensities are redshift 2 or 3. One would say that these already overdensities at redshift 2, 3 will become the top of the distribution in the local universe. But our relic galaxies are not found preferentially in the top of the plot. They are present at all masses.
it's a question of semantics.
Do you think so?
Yes.
Okay. Another thing that we can tell.
At high redshift, a large overdensity is something that would then create a group or a cluster.
Mhm.
It's already a large overdensity for that redshift.
But you have things like Perseus or Coma. Perseus is on the top of the distribution in the local universe.
Yes. Yeah. No, I agree.
So NGC 1277 happened to be found in Perseus.
Okay.
One will say, but according to this rationale, you have to find this relic galaxy only in Perseus-like structures. But this is not the case.
No, you show the distribution. You show the distribution.
Yes,
Yeah.
of course. So this is a very good point. So the thing is, the dark matter, Matt, please interrupt me whenever you want. So the thing is, the halo mass function has also exponential decay at high masses, right? So you can tell that the fact of finding many galaxies in this part of the plot is telling that these galaxies are more abundant on massive halos. That's true. But these galaxies also appear in halos that are not as massive. That's my only point. And I also agree with you
That's
that
fine,
at a
that's
certain
fine.
level there is some semantics.
I agree with that.
Perfect. But yes, I am not going to challenge here Orlando CDM. I will try though. And finally, the number densities of these objects are more or less 10 to minus 6 megaparsec cubic megaparsecs. So either by looking at the data point by ANA, we haven't found anything between redshift 0 and redshift 0.1, but then things are more or less flat from redshift 0.1 to redshift 0.3. Also in the Charbonnier paper that you did, Mark, and all the rest of the papers. And here I overplot the simulation by Kilis and Trujillo 2013, and because of things lie on the yellow part of the plot, it's telling us that the stellar mass of these objects has been modified only by 10% since their formation redshift. So these objects are real. Because of the number densities, we have a good idea that they are real relics, that they haven't undergone any important measure throughout their history. Okay? So to wrap up my presentation, I don't know what's the time. Okay. So just a view of the evolution of our current evolution of the most massive galaxies of the universe. So as I was telling you, we think that they are formed very early on because you have continuous merging that kind of replicates observationally a monolithic collapse. So you can have things which are forming stars at, let's say, 1,000 solar masses per year at redshift 4 or 5. And then we think that there is some quasar phase in which you quench the transformation of these objects, and the final remnant is something which is very compact, these red nuggets at high redshift, that throughout redshift they undergone a series of preferentially minor mergers with the companions, and the final outcome is the huge elliptical that we've seen in the local universe. In order to test that, for example, we have this, again, wonderful paper by Alex Borlaug, which has been published just 1 week ago or so, in which he is able to trace the envelopes of these galaxies in the Hubble Ultra Deep Field. And if you take these profiles and you plot the mass function of these galaxies between 10 and 50 kiloparsecs, you can tell that these massive galaxies are progressively joining the mass that you expect for the outskirts of local elliptical galaxies throughout redshift. This is also some work that we have done in the Hubble Ultra Deep Field in 2017. But the funny thing is that Alex's paper is able to reach 140 kiloparsecs for a galaxy which is at redshift 0.6, which is very, very remarkable. And of course that our beautiful elliptical galaxies are not so boring as we thought 10 years ago when I started my PhD, but now we have all these fast, slow rotators types that we were speaking about before. But besides of the typical slow, fast rotators that the people see in the Atlas 3D sample, you have also this idea about if you happen to fall very early on in a galaxy over density, you will become a relic. So this is another branch. Of course, it is very minor because you must think that, again, these are very massive galaxies. So we are in the exponential decay of the galaxy mass function. There are very few objects which are very massive in the universe. And here we are speaking about the exceptions of the something which is very scarce. So these galaxies are not very, very numerous. But still, they can tell us a lot about how our universe works throughout all cosmic distances. What my studies have shown that some of them are not falling in a high density environment or in a very high density environment. I like visualization. Exactly. But you can tell that several things are kind of isolated. They still have, you can tell here, more or less a disky structure, but a strange disk, as you say, Alex. Okay? But you have kind of two different channels, let's say. Of course, we must not remember about something that it's more numerous, that are these massive ultracompact galaxies. So things which are, again, like the relic galaxies, very massive, very small, but they are not all. However, these objects, which are really the red nuggets coming all the way from the high-redshift universe, and the massive ultracompact galaxies, which are red nuggets, which happen to be formed very late in the history of the universe, are telling us a lot about the physical phenomena that happen in the primeval universe. And finally, there will be the latest branch, which is here, ultramassive galaxies, things which are the top of the massive galaxies, things which lie in the center of very massive clusters, the brightest cluster galaxies, and things that are a bit more complicated about brightest cluster galaxies. That's why I came here to the ISE. This is why I was investigating these days with Ali Reza, with Jesus, etc. But I am not going to speak about these objects today. Just stay tuned for the future. So this will be the summary of my presentation. Massive ultracompact galaxies in general are these swollen disks with very high stellar densities. They reside in all kinds of galaxy overdensities, but we can puntualize a bit what it is an overdensity and what it is not. The important thing is that, of course, they are more numerous proportionally in galaxy overdensities, but they live in very different environments. And their number densities are very, very small. You need to survey, as Nacho says many times, a cube of 100 megaparsecs times 100 megaparsecs times 100 megaparsecs in order to find one of these objects. So finally, we were able to go from something which at high redshift sustains just, let's say, 100 pixels to something that we can tell with our own eyes and we can understand their properties. Thank you very much.
So
Okay, this is not about theory. I was curious to know, so you show that the compact galaxy are close to a larger companion in general in your images. Actually, in the images, in projection, they are in the halo of the larger companion.
Many of them, you're right.
Yes. So my question is technical, because I don't know. How do you measure the size?
How I measure them?
The effective radius.
The size of these galaxies. Well, I fit everything which is in the image.
But there is a background.
There is a background, but if your model of the companion is good enough, you can trust that you are measuring also the light well. You are able to blend the light from the two objects well enough.
Because I was looking at the position 2. So no,
Which one?
below. The second set. I was passed by. What is the? By this one.
Oh yes.
So the background galaxy is not regular at all. So how do you?
I did my best. I don't know. I don't know. I don't know which objects are more complicated, whether something like this or something which is extremely small.
Okay.
What I tell you is that I did my preselection of galaxies. With my preselection of galaxies, I was only managing, let's say, 200 objects. And when you have small samples, you can really go into the details of the galaxy decomposition. So I did everything manually as well as I could. But of course, there are always caveats about that. But this is a thing that we can learn from the new era of big data, right? When you have small samples is when you can really work on your sample. Oof, the boss.
is not working.
You are not allowed to speak here. No.
Okay, so I have a young spirit, so, so I'm not a. Well, that's fine. One clarification and one question. So the clarification is that you say that they are not expected, or the fact that you are finding relics in environments that are not so dense is weird, or you said explicitly at odds with the theoretical expectation. This is not correct. I mean, in the simulation, you expect 80% of the compact galaxies to live outside overdensities. So Luis Peralta, for example, in Luis Peralta paper, you can find that prediction. And I don't know whether
this is true. The first person which had an idea about these galaxies seems to live in different environment was in Luis' thesis. That's true.
Yeah. So, and I think also in the Springer paper, we mentioned also about some percentage of.
In the in the Springer paper, here, 82%, right? So all these red galaxies are living in the guys over here. Exactly.
Yes. Yeah. That total structure matter is dark matter.
But this is the dark matter halo of an object like this, which are in dark matter halos, which are bigger than.
So, but I mean, you can find. I mean, in principle, you can find up to 80% of these galaxies outside cluster. The point is that I think observationally, there is still no clear observation of one of these galaxies outside the cluster. So we have some candidates, and they are always in overdense regions.
We have applied for Megara time for our seven candidates for relic galaxies in order to have a perfect idea of the environment of these objects.
Yeah.
So using the MOS of Megara in order to use it as a redshift machine for all the companions and really to tell how massive are the environments where these galaxies live.
I'm saying all this because I think that we have more or less a good idea of how this object could survive in high density environments, but it's difficult to understand how they could be in low density environments.
Yeah, so we have several ideas about that. So first of all, here we are speaking about extreme galaxies, right? So why not, if we are speaking about something which is extreme, you happen to be formed very early on, and then you realize that there were not any other galaxies surrounding you, and you just happen to be in a abnormal.
The reason is because when you form something very massive at high redshift, you are in an overdense region. Because for forming massive galaxies, you have to be in a peak of mass in dark matter.
By chance, you happen to have no companions. So here we are speaking about, we surveyed 880 square degrees, and we only found 29 objects that were compatible with our selection criteria.
Okay, and then my question is, if you go back to your sample of galaxies where you saw the images of the galaxies.
Yes. And
there you go. So you see that in most of the cases you have a companion, right? The companion that you are looking at in those images are more or less of the same brightness or even brighter. So in principle, according to your survey, you should have redshift of these objects as well. Because otherwise you are not as complete as you say.
Yes, so for these galaxies over here, the big guys, we have redshift. In the cases that they are very minor, like many of these cases, no, we don't. Because the fact of our objects being very compact made them more point source-like, and it's easier to identify them.
In those cases where you have redshift, they are true companions or they are just projections?
They are companions.
So, you know, it would be very nervous because it seems too often to be just by chance. So it's probably something connected to a bias on the pre-selection of the sample. What do you think? The fact that the sizes that you have pre-selected are small because you have a super large survey.
The thing is, our pre-selection comes from sizes measured in Sloan for this image. Then, for things that were small in Sloan, just being small in one band, I reanalyzed those objects using kits. in which the PSF is 0.7, for example. In the other one, it's 0.7 arcseconds. So they are higher resolution images and 2 magnitudes deeper than Sloan. And I discard many objects, and at the end of the day, I only arrive with 29 objects in my final sample.
That's fine, but I mean, the point is, how secure are we about the pre-selection? So
I think that's fairly sure, because perhaps we missed some objects in our preselection because Sloan being not perfect for measuring sizes. So I could have missed some objects, but from the objects I have in our sample, I am fairly sure about their galaxy sizes.
no, I'm not. I mean, you look at the images and they are compact. That's fine, but the point is that because you are starting with a selection based on slow and sizes, whether they are just focusing on, they are pre-selecting some kind of galaxies like this.
That's why I'm telling you that perhaps in Sloan there were some problems, but the thing is 180 degrees, it is not easy to manage them in a proper way. First of all, yeah.
It could be. I don't know how. I mean, because the automatic tool for measuring sizes.
You have objects which are also isolated. It's true that there are not many, so perhaps this could signify a bias. But a bias will go in the other direction, right?
No,
that
depends
if you
on
are in the hell of
depends on how Sloan is treating the sky, for example. Because if over-subtract the light of the neighbor, then you go to a small size. I don't know. I mean, just guessing that biases on samples are the nightmare in astronomy. We are all affected by that, so it's really difficult to make clean samples. So having GAMA, why don't you run your codes in the entire sample automatically?
Because here we are speaking. No, of course you can do, but all these papers start as an adventure. Why don't we explore this data set, blah, blah. Here we are speaking that if you want to do things properly for speaking of sizes, we are speaking about analyzing millions of images. Yep. So, and super students. Fair enough. Thank you.
So one thing that puzzles me is, so yesterday we saw beautiful simulations about galaxies entering clusters and how they are stripped. So these guys are clearly potential candidates to be stripped. So how do you...
Well, but the galaxies which are easier to be stripped are galaxies which are not so massive, right? Because the potential wells are not so deep. When you have something as deep as 10 to 10, it is very hard to strip off their stars. But they are not that extended, right? They are 1-2 kiloparsecs. If you are a red nugget, you are not extended, and your potential well is very deep.
No, but if you were not a red nugget when you entered the cluster, and you ended up with a core, so what you are seeing is the core after being stripped.
But
for these particular guys which are in the halo of a supermassive galaxy, I don't know, theoreticians can tell better, but I don't know.
Chris?
So this is in simulations, or?
But for me, it's hard to think of this scenario. So I am not going to put fair enough. But my
So the
question,
point that it's observationally it's impossible to distinguish between the two.
why
So
not?
there's no. No, I mean, for this particular case, yes, because but for these guys, statistically speaking, it's impossible.
I don't know if it's observationally possible for this sample, but if you can get resolved stellar spectroscopy, right? If you can do the kinematics, you can look at the orbits of the stars. You'd preferentially strip things which maybe have high energy orbits or whatever, right? So you could actually look for some sort of anisotropy in the system. And they've done it for 1277, and it looks consistent with not having been stripped. But it's easier to find things which are stripped than things which are not stripped, right? So it's observationally. So yeah, that's one way to test it.
Hello. It would be nice if you could be more specific about the large-scale environment of these galaxies. This is the GAMA survey, right? So there has been, it's a paper published last year, Kraljic et al., and it's a collaboration between a French group and the GAMA survey. And they have mapped the cosmic web in terms of wars, filaments, and node. So you say these objects are in underdense region. I suspect they are in some rich groups, but it would be nice to see if they are in the filaments, close to them, or not so much, because some segregation effects have been found in the GAMA surveys in terms of the internal properties of galaxies, and you see that more massive and redder galaxies are closer to the filaments. And also the simulations show us, give us information about the accretion and merger history of galaxies, depending on where they are located. So I think the cosmic web is available, and it would
Could
be
you
really
repeat me
nice.
the first author of that paper?
Kraljic, K-R-A-L-J-I-C, et al.
Okay, but yes, it's very interesting. Thank you very much. By the way, before finishing, any questions from the students? Thank you.
Yeah, now it's time for me. Thank you very much. I would like to ask you how you've done your fitting exactly. Otherwise, I would ask many questions. So could you please just go and explain to us how you've done your fitting?
So you have the full details in the paper. But in a nutshell, what we did is we analyze all the objects within the image using single source profiles in order to, first of all, remove the contamination from the neighboring objects, and also because our objects are so small that more than a single Sersic function, it's impossible to be fit in so few pixels. I tried also to do some batch to these decompositions, but they are extremely challenging. Because of so few pixels, they are not very stable. A code, our code, the one I developed when I was a master's student. Yes, it's Galfit based, extractor plus Galfit. And using as PSF as an input, natural stars, and also, as I was telling you, shapelets, PSFs coming from the weak lensing group, from Conrad Quick and collaborators. But again, if you want to know a bit more of the details, I am more than happy to show the code, show you the paper. And the code, by the way, it's available via GitHub, if you want to use it. Yuska.
Hi, thanks for your talk. My question is about how did you quantify the masses of these objects, especially if they have a very nearby companion and there's a lot of contamination from a large companion. So how do you get these masses?
Very good question indeed.
Thank you.
So the thing is, because of they are part of the GAMA survey, the people already have masses about these objects. The masses are very simple. So there was a paper, can't remember who was the author, in which they saw that the best proxy for the mass in the GAMA survey is the I-band flux for these objects. So it is just I-band flux times mass to light ratio for them that we derive empirically. However, of course, as you have said, the light from our target audience are contaminated by the neighbors. So once I have the Gulfit flux from these objects, I took it and I multiplied for those mass to light ratios in order to have new mass measurements. And this way also I removed part of the sample because they were not massive enough. So it is not perfect mass derivation, but it is better than just simply using what it came from the catalogs.
Okay, so I think, is there any last question? No? Okay.
Coffee.
So let's thank Fernando again.
Thank you.